and welcome to Physical Geography, Topic 1. Now, Topic 1 covers hydrology and fluvial geomorphology, and this is going to be your very first video on open versus closed systems. So just a quick introduction to some of the vocabulary that you see here. Hydrology and fluvial geomorphology, two very large words. So hydrology, the study of the movement, distribution, and quality of water. Hydro, think water, ology, study of. Fluvial geomorphology, this is the study of the processes that operate on a river system. How do rivers form? How do they move? How do they do the things that they do? And so I wanted to give you some idea of what those two terms mean before we move forward. So the very first section of this AICE geography, topic 1, is called the drainage basin system. So we're going to talk a little bit about the drainage basin system. So first let's talk about what an open and a closed system is. If you think back to physical science, whenever you might have taken a physical science class, we talked a little bit about open and closed systems in there. So a system is a group of interacting elements that have a common purpose. So systems, we have a global system, the Earth, your human body system, an air conditioner system. These are all systems of interacting parts that have a common purpose. Now we see two types of systems. We see an open system and a closed system. Now an open system allows the interactions between its elements and the environment. This allows energy to flow through evenly, distributed coming in and out. So an open system is kind of like an open door. You can go in and out. A closed system does not allow interactions between its elements and the environment. So this is where your door, all the windows are absolutely shut. The system works on its own and does not allow any sort of interaction with the outside environment. So an example of a closed system would be an air conditioner. And an example of an open system would be a car. In the case of the car, you have air flowing through your air filters. You have things coming into the system from the outside, whereas an air conditioner runs specifically on its own. It does not allow any sort of energy coming from the outside. So we have to keep this in mind when we're talking about the global hydrological cycle. Now, you know this better as the water cycle. And this is probably something, if you took biology last year, you might have seen this picture. So the global hydrological cycle, the water cycle as a global scale is a closed system. It does not allow energy from the outside to come into this particular water cycle. All the water that we have on Earth is within this closed system. So this might be something sort of familiar to you, where we have condensation. I'll start over here on the right-hand side. We have this condensation over here. We have transpiration coming from the trees. So that's your evaporation basically coming from the trees. Your condensation creates these clouds, which then will rain. That's your precipitation. We have surface runoff, and we have infiltration. And we're going to talk about a lot of these terms as we go through this first section. Then we have the rivers and the surface waters. Streams, lakes, your oceans. We also see groundwater flow. So this is the water that's flowing underneath the ground. And then once again, we have evaporation turning into these clouds. We have this condensation. And then we have the transpiration, again, coming from the trees and the plant life. So global hydrological cycle is a closed system. It does not allow any sort of energy to enter it, does not let any energy leave it. So within the global hydrological cycle, the water cycle, we see some of these terms here, and there's a whole bunch of them. And you're going to hear terms called input, output, store, flows. Now, if you put this all together as one giant circle from the water cycle, we have input. The input is that precipitation. So any time of rain, snow, anything like that, that's your input. We have outputs as well. This is where we have that water leaving back, becoming kind of like becoming condensation again, and in the form of evaporation. Evapotranspiration. Now, this is just a fancier term for transpiration, that evaporation from plants. River runoff would also be an output. Leakage. Now, this might be leakage from, let's say, from a lake inside the ground, or it could be from the ground up into a lake. So we have different types of leakage. We also have places called stores. Now, this is where we have water that's actually stored either on the surface, on plants, or below the surface. So think of it as in terms of a store. We have groundwater stores. We have channels. These could be any sorts of rivers, from little streams to really large rivers. Soil moisture. The soil holds on to some of this water beneath the soil and maybe even just slightly close to the surface. Vegetation. Your plants actually hold on to a lot of water as well. They use the water for specific things anyway, so you can see why it likes to hold, or the plants like to hold on to water. The surface can also hold water in forms of lakes, oceans, some of your larger bodies of water, or even like little ponds. And things called interception. And now we're going to talk a little bit about that. But that's basically where you have large amounts of trees kind of intercepting the rain or the precipitation from the surface, or I shouldn't say from the surface, from the sky to the surface. It almost captures it, if you will, in sort of like leaves or some plants. And finally, we have flows. Now think of flows as where water actually moves. And we're going to talk about these throughout the lesson, but just know that these are things called throughfall. We have surface flow or overland flow. You're going to see the two words combined in this lesson. We have through flow, base flow, percolation, infiltration, and channel flow. Now, the drainage basin is an open system. So think of your global cycle, your global hydrological cycle as a closed system, and think of your drainage basin as an open system. Now, a drainage basin is something like a watershed. It's an area of land that collects the water and kind of distributes it to places that need it. There's several different watersheds throughout Florida, throughout this little area, and throughout the globe. And we're going to start to do a case study on something that's more related to us here in Sarasota. And this is an excellent example of a flow chart of the global hydrological cycle. This is something that you want to make sure that you understand, and we're going to go through each individual one in terms of the water cycle and in terms of Sarasota. So just understand that in blue, we have our inputs, and this is where we get precipitation. This greenish kind of color, these are your stores. So these are all places that water is actually stored, either on the ground or below it. Transfers, these are your flows. So anything in orange, this is where water is actually being moved from one place to another. And your outputs are this brownish kind of color. This is where it now basically leaves this particular part. So while this whole thing here is considered the part of the global hydrological cycle, think of your drainage basins, the very little tiny spots around the globe, as an open system. We do have energy and water coming into individual drainage basins, but as a global hydrological cycle, we do not have energy or water flowing in and out from an outside source. So let's kind of take a look at watershed a little bit closely here. I have a picture here of basically the Mississippi River watershed. And this is a huge basin, the drainage basin of the Mississippi River. Now, I chose the Mississippi River. It might be something that you are more familiar with. So the term watershed, this is an area of land that collects, transports, and stores precipitation in the area, and it includes both surface and subsurface waters. So it includes in this Mississippi waters here, the river itself, all its tributaries, and any of the little rivers, the lakes, the streams that might not even be on this map. So this whole thing here is the drainage basin, or also known as a watershed. Now, we're going to talk specifically about Florida soon, but just know that Florida actually has several management districts, several watersheds around Florida. And here in Sarasota, which I guess we're sort of like right around here, we are in the Sarasota Bay watershed, and we're going to talk a little bit more about that. So a drainage basin can be another name for watershed. It's a subsection of a watershed, also known as a catchment area. There's a lot of different terms to be used for watersheds. And this is usually identified by a main body of water into which other water flows. So around where we are, we have several different rivers that kind of flow into Sarasota Bay. And Sarasota Bay is where all that river flows into. And we're going to talk about that very shortly. Finally, to kind of discuss a little bit about rivers, you do need to know about two terms, the velocity and discharge. Now, velocity is just another fancy word for speed. So when you read this definition, just kind of think of the velocity of a river as its speed. Now, velocity is a measure of the downstream distance that water travels in a given time. So distance divided by time. And technically, velocity has a direction to it. We really would know the direction of it as well. Now, the velocity is influenced by a couple different things of the river. Channel shape. What shape is the river actually? Can we see it? And I have a picture here of a couple different types of channel shapes that we might see. You might see something kind of like a rectangular shape, something a little bit more trapezoidal, or maybe something like a bowl. We see this a lot in some of the rivers. Maybe it's a V shape, convex. So the channel shape determines its velocity, along with its gradient. The gradient is basically based on gravity. So how steep is that particular channel? Is it really steep? We're going to have a greater velocity. If it's not really steep at all, it might go pretty slow. And the roughness. Basically, along the bottom of these beds, how rough is it? Are there a lot of rocks? Is it fairly smooth? So that will also determine its velocity. So for example, water will move slower and with greater turbulence near a channel's bed and its banks because friction is greater. So along the bed and the banks, the bed tends to be right along the bottom. The banks are going to be its sides. If there's a lot of little rocks or bigger rocks, there's a higher amount of friction, which means the water is going to move much slower. Whereas if it's pretty smooth, the water is going to go pretty fast. So these types of the shape, the gradient, the roughness of the river is going to determine how fast it's actually moving. Now we also are concerned with the discharge of a river. The discharge is the volume of water that passes a particular point in a given period of time. So how much water is passing through that river? Now, sometimes if the river is fairly large, it's going to have a large amount of discharge. If it's a smaller river, maybe a tiny stream, you might get smaller amounts of water. So its discharge is going to be much smaller. Now, this usually increases as we go downstream due to the addition of water from other sources. So as you go farther downstream, and let me go back to this watershed picture so you can see. So this is the picture of the Mississippi Basin, river basin. And the Mississippi River flows south. So it starts up here in the north in the United States and it flowed down towards the Gulf of Mexico. Now, as it's flowing downstream, it's going to actually increase its discharge because it has more water downstream, down here towards the Gulf of Mexico, than it does up here. So the Mississippi doesn't have any tributaries up towards the top, that major ones anyway. But as we go downstream, notice all the rivers coming from other places in the United States are connecting to that Mississippi River. And it's going to increase the discharge, the amount of water, and it might even increase its velocity, it might increase it, the speed of it as well. So velocity and discharge are very important to understand as we move along and so we start talking about some of the other things about rivers. So velocity is the speed, discharge, the volume or amount of water.